Welcome. In this video, we'll explore the essential role of HPLC columns in chromatographic separation. The HPLC column is often considered the heart of the separation process, as it's where the chemistry and physics of separation truly happen. Understanding how columns work and what factors influence their performance is crucial for anyone aiming to achieve reliable and reproducible results in HPLC. Throughout this video, we'll break down the key parameters, materials, and best practices for using and maintaining your columns. Let's start by understanding why the column is so central to HPLC success. Controlling a separation means understanding and managing the chemistry and physics inside the column. Different columns can vary in their plate number, band symmetry, retention, band spacing, and lifetime. These factors directly affect the quality of your separation and the reliability of your results. By choosing the right column and maintaining it properly, you can optimize your HPLC performance and minimize troubleshooting. Let's look at what makes each column unique and how these differences impact your analysis. Let's break down the main parameters of HPLC columns. The container itself has a specific diameter and length, and is made from materials chosen for durability and chemical compatibility. Inside, the packing materials are critical. They determine particle size, shape, surface area, carbon content, and the chemistry of bonding. Features like silanol content, end capping, and purity also play a role in how the column performs. Each of these parameters can be fine-tuned to suit different analytical needs, making column selection a key step in method development. HPLC columns come in various dimensions, each suited for different applications. Analytical columns typically have an inner diameter of 0.3 to 0.46 cm and lengths from 3 to 25 cm with particle sizes between 3 and 10 microns. Semi-micro, semi-preparative, and preparative columns have their own standard sizes, optimized for sensitivity, throughput, or preparative scale. Choosing the right dimension ensures you get the best balance of efficiency, speed, and sample capacity for your analysis. Silica-based packing materials are the most popular choice for HPLC columns. They offer narrow pore size and diameter distribution, high mechanical strength, and the highest efficiency. Importantly, silica doesn't swell with changes in solvent, ensuring dimensional stability. However, the surface acidity of silica can cause problems when separating basic compounds, so it's important to consider your sample type when selecting a column. Polymer-based packing materials, often made from divinylbenzene cross-linked polystyrene, are valued for their longer lifetime and lower back pressure. They can operate over a wider pH range and are suitable for separating highly basic solutes at high pH. However, these particles can swell, especially in gradient elution, which may reduce efficiency. Polymer-based columns are also more tolerant of higher temperatures, making them versatile for challenging separation. Particle size in silica gel packing has a direct impact on column performance. Larger particles result in lower back pressure and are more economical, while smaller particles offer higher efficiency and longer column life. For most analytical columns, particle sizes between 3 and 5 microns are standard, balancing efficiency and run time. Semi-preparative and preparative columns use larger particles to handle higher sample loads. Silica gel particles can be either spherical or irregular in shape. Spherical particles provide higher efficiency, longer life, and greater mechanical strength, but come at a higher cost. Irregular particles, while more economical, tend to generate higher back pressure and broader bands. The choice between these shapes depends on your budget and the performance requirements of your analysis. Most silica gels used in HPLC are porous, with pore sizes typically ranging from 70 to 120 angstroms for analytical columns. Larger pore sizes, such as 300, 500, or even 1000 angstroms, are available for separating large molecules like proteins or synthetic polymers. The choice of pore size is critical for ensuring efficient separation of your target analyte. Surface area of silica gel is closely related to its pore size. Narrow pores 70-120 A-ring provide a high surface area, typically 150 to 400 m2G, ideal for small molecule separations. Wider pores 150-1000 A-ring offer lower surface area, suitable for macromolecular separations. Selecting the right surface area ensures optimal interaction between your analytes and the stationary phase. Carbon content in the packing material influences the column's retention capability. A typical range is 12% to 20%, which provides strong retention for a wide variety of analytes. Consistent carbon content is also important for reproducibility between batches, ensuring that your results remain reliable over time. Chemistry of bonding in silica gel packing is a delicate process. It involves controlling the diameter, shape, and porosity of the particles during preparation. The bonding process attaches functional groups such as C18 chains to the silica surface, which determines the column's selectivity and retention characteristics. Proper bonding chemistry is essential for achieving high performance and reproducibility. Silane coupling reagents are used to bond functional groups to the silica surface. Monofunctional silanes such as CLC, CH32R are commonly used for their reproducibility. Trifunctional silanes and alkoxysilanes are also available. The choice of reagent affects the stability and performance of the bonded phase, with monofunctional types preferred for consistent results. Even after modification, residual silanol groups remain on the silica surface. These groups can strongly absorb amine compounds, leading to peak tailing in chromatograms. Managing residual silanol is important for achieving sharp, symmetrical peaks, especially when analyzing basic compounds. Encapping is a process that reacts residual silanol groups with small silanes, such as trimethylchlorosilane. This increases the coverage of the silica support, minimizing unwanted interactions with solutes. Proper end capping results in more consistent and reliable chromatographic performance, especially for sensitive analyses. Columns with proper end capping show better peak shapes and less tailing compared to those with insufficient end capping. This is especially important for compounds like propranolol, acenophthene, and amitriptyline. Using well-end-capped columns ensures more accurate and reproducible results across a range of analytes. Purity of the silica support is crucial, especially when separating basic and highly polar compounds. Trace metals in silica can interact with analytes, causing asymmetrical or tailing peaks or even complete retention. Metals like aluminum activate silanol groups, making them highly acidic. High-purity silica minimizes these issues and ensures consistent performance. Shimpack VPODS column is a high-performance example, featuring entirely porous spherical silica particles with high purity. It has a particle size of 5 microM, a pore size of 120 A ring, and a specific surface area of 410 m2G with 20% carbon content, end capping, and low trace metal content. This column is designed for reproducibility and robust separation. Quality certificates like those provided for Shimpack VPODS columns guarantee that each batch meets strict specifications for particle size, pore size, surface area, carbon content, and trace metals. This documentation is essential for regulatory compliance and method validation, giving users confidence in their analytical results. To get the most from your HPLC column, always condition new columns at a low flow rate before use. Flush with a strong solvent after each day's use to remove absorbed materials, and never leave buffer solutions in the column. Cap both ends when not in use to prevent drying, and always use a guard column for added protection. Guard column acts as a sacrificial layer, protecting your main analytical column from contaminants and particulates. It should have the same stationary phase and packing technique as the analytical column. If the packing differs, separation and protection capabilities decrease. Using a guard column extends the life of your main column and maintains separation quality. Hydrophobic collapse occurs under low organic solvent conditions, typically below 5%. The hydrophobic alkyl chains of the stationary phase fold down on the silica surface, reducing their ability to interact with solutes. This leads to a loss of retention and can compromise your separation. Maintaining appropriate solvent conditions prevents this issue. Columns can fail for several reasons: chemical attack of the packing material, binding of materials to the column, pressure increases, and formation of column voids. Recognizing these failure modes helps you take preventive action and extend the life of your columns, saving time and resources in your lab. Low pH below 2 can strip the bonded phase, exposing free silanol groups and increasing polarity. High pH above 8 dissolves silica, forming end voids. High temperatures and high salt concentrations also accelerate column degradation. To maximize column life, keep pH below 7.5 and avoid extreme conditions. Nonpolar organics, inorganic cations, and charged organics can bind to the column, altering its running characteristics. Contaminated water is a common source of these problems. Proper sample pretreatment and using dedicated columns for specific analyses help prevent these issues and maintain column performance. Washing the column is essential for removing nonpolar contaminants. When using a buffered mobile phase, always wash out the buffer with the same mobile phase minus the buffer first. Then, wash with acetonitrile or methanol for about 20 column volumes to ensure thorough cleaning. For reversed phase columns, a stepwise cleaning protocol is recommended. Start with mobile phase without buffer salts, then wash with methanol or acetonitrile, followed by THF or isopropanol, hexane, and back to methanol or acetonitrile. This sequence ensures removal of a wide range of contaminants and restores column performance. All columns have a maximum operating pressure. If pressure increases, identify whether the issue is with the column or the system. Pressure can build up at the inlet frit, outlet frit, or within the column bed. Regular maintenance and proper filtration of buffers and samples help prevent pressure problems. Always filter buffer solutions and samples through a 0.2 or 0.45 microM membrane filter. Avoid sudden changes from buffer to pure organic solvent, or vice versa, as this can cause precipitation and pressure problems. Use an intermediate solvent for transitions to prevent plugging and maintain smooth operation. If you encounter pressure issues, wash the column with a suitable solvent. If necessary, open the column end, carefully remove and sonicate the filter or frit, or replace it. Washing the column in reverse at a low flow rate can also help clear blockages and restore normal operation. If only a small section of the column is contaminated, you may be able to remove and repack just that part with clean packing material. Always use the same size and type of material as originally used in the column. This approach can extend column life and reduce costs. Column voids, especially center voids, are fatal to column performance and cause split peaks. Mechanical shocks like dropping the column, banging it around, or releasing pressure suddenly can create these voids. Every peak may start to look like a rabbit ear, signaling a serious problem. To prevent column voids, never drop your column or let it bang around in storage. Avoid sudden pressure changes, do not switch to immiscible solvents abruptly, and never reverse the column flow or jump flow rates suddenly. Gentle handling and gradual changes are key to maintaining column integrity. Summary: mastering HPLC columns involves understanding their construction, choosing the right materials and dimensions, and following best practices for use and maintenance. By taking care of your columns, you ensure reliable, high-quality separations and extend the life of your equipment. Thanks for watching, and remember, a well-maintained column is the foundation of successful HPLC analysis.